Hello, apes, and welcome to screencast number 3 on Chapter 2. And Chapter 2 is the Earth's physical systems, matter, energy, and geology. So right now we're just reviewing a little bit of chemistry that we need. And we had been talking about ionic bonds and covalent bonds. So here's the definition. Ionic bonds have electrons that are transferred between the atoms, and covalent bonds have electrons that are shared between the atoms. Again, this is review, so I'm not going to spend a lot of time on it. If you're not certain about this at this point, then it's your responsibility to go and look those up. Okay, so I think we skipped something here. All right, so here is ionic bonds, the sodium and chlorine, and we can see how cool is that. I don't even have to point to it. That the electron is going to be transferred, and you're going to get a sodium ion and a chlorine ion. It's a sodium ion because it has a +1. There's more protons than there are electrons. And this one is a negative ion because it has a -1. It has more electrons than it does the protons. Okay. In covalent bonding, let's get this to right click. Maybe that one's not going to work like the other one did. Okay, in covalent bonding, right click and select play. It keeps going back. Bear with me here. Right click and select play. Here we go. I selected play. Oh, isn't that cool? Wow, it's actually working. All right, since it's not working, the covalent bonds, they're going to share the electrons, and when they bond together, these electrons are going to, here we go, it's going. They're going to share those electrons where they're going to stay in the orbit. This one may orbit this hydrogen and then come and orbit that hydrogen and continue around like that. Okay, glad we got it to work. Now we can't get it to advance. Oh, technology. So here's more covalent bonds. Let's see if we can get this one going with the oxygen. And there we go. Ooh. All right, so they're going to share those electrons, and that's a double covalent bond. Okay. Here's some more examples. Methane. It's not letting me advance. Okay. We know that water, when I had biology with you, we know in Chapter 2 we talked about water's unique properties to be polar, to have a slightly positive side and a slightly negative side. And that because of that polarity, hydrogen bonds would form. And this is where oxygen from one water molecule is going to attract the hydrogen atoms of another water molecule. We know that those forces were responsible for cohesion, as I've already mentioned. And remember the Jesus Christ lizard that I showed you that could go across the water? It's the reason why insects can walk across water. If you didn't see the Jesus Christ lizard, you have to YouTube the Costa Rican Jesus Christ lizard and see it walk across water. It's really cool. Water absorbs heat is another property that we did not talk about in general biology, but just think about 73–75% of the Earth's surface is covered with water, and the sun's beating down on that daily, especially in the summertime. And it absorbs a lot of heat. It can hold a lot of heat before it begins to be at a temperature that is not viable for living systems. So it can hold this heat with very small changes in temperature. to stabilize the systems and the organisms that live within in the water, and helps to regulate the climate. So water is very essential to our being alive and being here. So here's that example. This is the slightly positive side. This is the slightly negative side of the water molecule, and because they're opposites, the oxygen side is going to join with the hydrogen side and going to form these hydrogen bonds. You've seen this illustration before, this model before. As well as some of the properties of water, ice is less dense, therefore it floats on water. Because it floats on water, it actually helps to insulate lakes and ponds in the wintertime so that organisms can survive and live in the ponds. They will actually go down deeper in the water where the temperature of the water is like 50 degrees. And that might seem really cool to you, but it helps to slow their systems down so that they don't need as much energy and they can survive the winter. Some will even hibernate under the mud, under the freeze line of the mud. Water is also essential for dissolving molecules that we need, that are essential for life. Water dissolves sugar, water dissolves salt. These are things that we take in and we consume that we need for cellular activities in our bodies. So here we go. If you want to get an idea about why ice is less dense, here is a huge chunk of ice, and this is what its molecular arrangement would look like compared to water, which is much closer together. So that's what makes it less dense. There's more space. When it freezes, it kind of pulls it apart. Oops. Okay. So that's the structure of water that you're seeing here, and we're going to try the right click and play thing again. Okay, so you're seeing that the hydrogen has the attraction to the oxygen in the way that it bonds in the covalent bonding. Okay, also the way that water splits is also important in determining pH. And hopefully these things are coming back to you and you're saying, oh yeah, Mrs. Saunders, I'm remembering this. So 1 out of every 550 million molecules of water goes through a split. And let me just kind of illustrate this here for you. So we've got our water molecule, our Mickey Mouse water molecule, our hydrogens here, and our oxygens here. And we've got a pair of electrons being shared and electrons here being shared. You've probably seen this before. So when it splits, what happens is the one hydrogen, and I'm going to just make this a little bit bigger, loses the electron because the oxygen and the other hydrogen keep those electrons. So since that loses an electron, it becomes a hydrogen ion. And since this gains the electron, this becomes a hydroxide ion. And it is the number of these hydrogen ions and hydroxide ions that determine the pH of a solution. So when we think about the pH scale ranges from 0 to 14. And it tells us how many hydrogen ions we have or how many hydroxide ions we have. So if we're an acetic solution, acetic solutions are going to be on the scale 0 to 6, so less than 7. The closer we are to 0, the more hydrogen ions we have. The further we get to 6, the less hydrogen ions we have. Okay, so that's how the scale runs. So if we have a lot of hydrogen ions, then we're an acid. That's going to make us an acid, and we know that the characteristics of acids are kind of like sour to taste. Your lemon juice, your hydrochloric acid. If you had acid reflux, you know that that's like a yucky taste. Basic solutions, on the other hand, are going to have more hydroxide ions, and they are on the pH scale greater than 7. So they're going to be going from 8 to 14 on the scale. And this time, the more hydrogen ions we have, we're going to be 14. We're going to be closer to 14. The less hydroxide ions we have, we're going to be on the side of 8. 7 is considered neutral because it is equal in the number of hydrogen ions and equal in the number of hydroxide ions. So that's what pH is. You might recall from chemistry that the pH scale is logarithmic. So if a substance contains a pH of 6, it contains 10 times as many hydrogen ions as a substance that had a pH of 7. So if it has a pH of 5, it contains 10 times more than it did when it had a pH of 6. Okay, so it increases as it goes down by 10 times or up. So here is your pH scale, and you can see pure water on the scale is neutral, and if we're basic, seawater is considered basic. The soap that you use to shower with and wash your hands with, that is a base. It's kind of a midline base. Your cleaning supplies like ammonia that you would use to clean is getting to be a stronger base, and sodium hydroxide is one of the strongest bases. Okay, on the other end of the scale, normal rainwater has an acidic pH, and yet acid rain, and that's rain with pollution, has even a stronger pH of 4. Lemon juice is down by 2.5, and stomach acid, really strong. This can actually eat the paint away on your car if you were to put it there. Car battery acid is one of the strongest at 0.5. And notice, the colors are important. Anytime you have a base, it's blue, and anytime you have an acid, it's red. Okay, so that is consistent. That's what we use in determining that when we use like pH papers. Okay, so back to the idea of matter. Matter is composed of organic compounds, and we know that organic compounds are anything carbon-based, where carbon is the backbone of that chemical compound, and they can form the large macromolecules that we talked about, like proteins and carbohydrates and lipids and nucleic acids. Okay, organic chemistry is the chemistry of biology because it's the chemistry of life. So carbon can join with other carbon atoms, as well as hydrogens and oxygens and phosphorus and sulfur and nitrogen are the most common elements that can bond in with carbon in organic compounds. Inorganic compounds are the compounds that lack carbon. They don't have that carbon-to-carbon bonding. They don't have that carbon as the backbone that we've talked about. So that's the difference between the two. Our inorganic compounds, that's what we're going to find in a lot of our non-living things, like our rocks and some of our soil and deposits, mineral deposits and things like that. We need to remember the word polymer, and polymer is just simply a long chain of carbon molecules. It's made from, if you remember the term, and hopefully you're saying, oh, I remember that, Mrs. Saunders, monomers. And monomers are smaller compounds that, like glucose, that can form these chains to make polymers, like a polysaccharide or like a protein. And the process of making polymers is called polymerization. Okay, so these are all terms you heard before.